Let's talk about MEMS foundry and more broadly semiconductor foundry. I will review how products are made in a foundry, how it works, and how much it costs to run a foundry and how much money it can make. So, I have been working in two US based foundries in Austin, Texas, and Silicon Valley, California. And a foundry is a place where silicon products are made. It consists of equipment and a clean room, of course. And the size has to be pretty big for it to contain many types of equipment in there. The mission of a foundry are the following to develop production process of a first article NPI, new product introduction, often in collaboration with customers. Without a customer, you don't make a thing, right? You don't develop something and then find a customer. You have to find the customer first and then make the process for them. So it's a dance of two parties. Then you produce a set products for customers. The point of a foundry is to eventually make them in your foundry. You don't just develop the process, but without the customer, there's no process. Without the process, there's no production. And so it's a chicken egg problem of highest degree of cost. You have to find high volume products and maintain your edge so that you can have a pricing power and so that you can keep the roof on and keep paying the rent. The goal of a foundry is the following to make efficient, high yield process to produce satisfactory products for the industrial customers. And you need to have room for scaling. And it is important to reduce the cost, reduce the cycle time so that you don't spend, you know, 6 months from the start of a wafer to the finish. You want to do it as soon as possible, as fast as possible. And then you want to maintain your technical know how and edge, increase the yield, have profits. It is very important ultimately to have a good team and culture. Without the team and culture, a foundry would not work. I have been in foundries, companies that does not have a good team and the managers micromanage and they're arrogant. They really don't know what they're doing, but they manage everything by decree, never go to the clean room. So it's very important to have a good culture. Without a good culture, I don't believe you'll have a satisfactory company for long. In a foundry, you see a lot of people with bunny suits, but they play different roles. Some of them might be operators, some of them might be engineers who develop products, and some of them might be technicians. So just because everyone is in the same bunny suit doesn't mean they play the same role. And there are many layers that you must develop to make a product, and it is very critical to have good people who know what they're doing, and you have to keep them and also try to keep them happy. Let's talk about the money. A foundry operator may have to borrow money for growth if necessary. It's not just enough to use your internally generated revenue and profits. The semiconductor industry is notoriously cyclic, and in some days you may have the 5G, you may have the AI, and those booms are typically interjected with busts. It is very important to keep a healthy operation for long. Otherwise, you're going to be moving from place to place. The gross profit margin is typically 45% or better, but the real profit will be much lower than this, right? Your ability to claim your profit depends on your bargain power with your customer, and certainly it comes with your leadership position in your industry. Here are some of the key KPIs, key performance index. On-time delivery of first article, wafer yield of, or often called line yield. The die yield is how many dies comes out of a wafer. And the defect on arrival report is important. This is what the customers report to you. If they receive defective products, they will file a DOA, and this count against your Six Sigma performance. Cost is relentless in this field, right? Equipment are very costly and they take time to order. If you order a new equipment, it typically takes about 2 years to arrive. And the wafer size change. When the wafer size change from 4-inch to 6-inch to 8-inch, then all the equipment are rendered obsolete, and you have to sell them 5 cents on a dollar. Chemicals, consumables are expensive. Utility is expensive, right? If your utility is down for 1 second, then all the wafers are shot. So everything is very expensive. In a clean room, you have a typical scene like this, where you have wafers that are waiting to be processed at a particular bay or station. Those are 12-inch wafers and 8-inch wafers. They have their numbers, and the processing is what gives the wafer fab revenue. In this particular case, the processing here is not even for its own use. It's actually for other factories. Other factories just ship you something for you to grow a certain layer and ship them back. There are many large and expensive equipment. This applied material tool might cost $2 million to buy new. And it is even very expensive just to replace them. And those are reactive ion etchers, RAE machines with multi-base. So there are different kinds of customers coming into the clean room. There are customers that sell the products you make for them, or customers who make their products, but they use your products as part of the production process. There are different scales of customers. Some makes 100 wafers a month. Some makes 1,000,000 wafers a month. So obviously, a foundry company that makes 100 wafers a month can already go public in US. The customer types, some of them are startups without their clean room. And but they cannot just go to TSMC, those large foundries, because they don't have enough orders to occupy them. And sometimes you have big companies, small groups in big companies seeking some capacities that they cannot get from their own company. So the MEMS integrators have a very important role. And as their name suggests, they integrate. They deal with the business team, marketing, design team, and scheduler team. They work with the direct labor team. It's called direct labor because the labor is counted as direct cost to the customers. Those are workers and operators on the floor. And integrators work with module team. Even though you may have knowledge about different modules such as metrology, lithography, grind, planarization, and plating, you still have to work with teams that are dedicated in their silos. So in the module team, there are leads, engineers, and technicians. The work of an integrator is to do experiment or qualifying lots. Those are called E lots, engineering lots, or PQ lots, production qualifying lots. The lead lots are created to identify any potential issues that may be attributed to a new product or a new process. The goal is to deliver first article devices and get feedback from the customer on time. the customer give you feedback and you keep on developing this. Sometimes this can go on for 3, 4 years. I have had processes where after 3 years, the product is still not qualified by the customer. But ironically, the life cycle of the customer's project is only a year. So that means you're late. Uh, a lot of times the wafers are uh, physically placed in a bay and they may get lost and they may get hidden somewhere. And this is me looking for wafers and lost at night because you cannot ask the operators to look for them for you. They won't. And this is part of the life, and actually part of the life I don't quite like. But in a smaller fab, that's life. Facility consists of a lot of piping and chemicals and so on. Those are not the jobs of the uh, operators. Those are the jobs of the facilities maintenance team. You have to develop what's called routing. A routing is a detailed step-by-step description of the process that a wafer goes through. The routing consists of recipes, consists of machine recipes that are set in the machine, and each machine recipe may have their own detailed parameters. So it is very important for an integrator to know the routes, knows the recipes, and the detailed parameters of processing. This is a picture of how many masks are on deck in a clean room. And there are quite a lot, and the operators have to find the mask and use the right mask. The instruction of which mask to use comes from the integrator. Now, why is a foundry different from a real factory and or a academic lab? Now, in a lab, you can work alone. You do everything by yourself. But in a foundry, you have to work with people. There are different people mining different modules. So the number of people involved is different. But it's also not a straight up factory. In a straight up factory, you make commodity products that everybody can make, right? You're basically contributing to the labor. Here, you also contribute intellectually to make a unique product. Here are some of the terms that we often hear and see. Products, obviously, it's a name of a customer's uh, end product, and it's typically given uh, a assigned name uh, so that it doesn't expose the true nature of who the customer is and what it is about. The production team and the engineering team are separated. The engineers are typically are not in production. It's actually not allowed. The engineering team help with production, but they also make NREs, non-recurring engineering. The different casts in the on the floor include engineers, technicians, and operators. Now, when you see a picture of people in bunny suits and clean rooms, they may have different roles. Right? This people might be the operators. This might be a technician or showing, or this might be some kind of training. Uh, the engineers are not supposed to do the works of the operators, even though you can, because you're taking away their job. The production labors are actually quite abundant, unlike what people think. In the United States, you can pay $20, $30 an hour and have a team of operators work for you. The customers that you serve will pay for the labor cost of these operators. So it really have nothing to do with the cost of labor. Whatever cost would be absorbed by the customer of the foundry. In a clean room, you have different modules, different bays. This is a plating bay, and this is a lithography bay. There are operators, technicians, machines. Machines contain recipes, and the recipes are the ones that they see on a computer screen when they approach their workstation. Now, there's also the marketing team, the business team. The business team never go into the clean room. They probably don't understand too much about semiconductor physics, but they deal with customers. They get orders coming on a schedule. So this can sometimes create a problem because a marketing team may get the engineers some headaches by accepting some request that they shouldn't be accepting. Now, the next term is process and routing. In a process and routing, you have to lay out the step by step description of what to do with each of these steps and multi layer structures. And the silicon, of course, they all have on the base, they always have the silicon transistor, but on top of the transistor, you have to have many layers of routing and wire leads, and this is where the processing gets very sophisticated. Die map. On a wafer, there are dies, and the IT department set up a die map so that each die, each unit can be tracked. The modules and integration work together. There are several different modules, at least lithography, planarization, uh, plating, metrology, at least. There could be a lot more. And when you have a wafer that come out with some defects, such as scratches or particles of unknown nature, the integration team will need to identify the source and identify if they should be cause for scrap or not. And this is actually maybe 60% of an engineer's job in a foundry. This is why they're getting paid. And they also decide what is proper CD, uh, critical dimensions to measure, where to measure, and things like that. This is a box of wafers, of 8-inch wafers. They are stuck together. Uh, the goal of this integration team is to develop the routing, develop the process, so the operators can take a box from one station to another without your involvement. The integrators are not involved in detailed processing. And the wafers are in a machine that process uh, to a certain recipe, and the recipes are decided by the integrators through collaboration with modules. So on a die, you also have patterns. The layout and design are typically made by a different person in charge of layout and mask making. The CDs are measured um, and then plotted. The wafers are inspected at different stations, and the red ones are scrapped dies, and the green ones are the accepted ones. In this particular case, the wafer yield is already dropped to below 50%. Now let's talk about whip and lots, right? Whips and lots are the bread and butter of a foundry. The foundry moves wafers, and the wafers in process, called whip, are tracked on a daily basis, hourly basis. The whip status, each wafer, each lot is uh, looked carefully, and if they are stuck, if they are scrapped, if they are stopped, it is all cause for concerns. A wafer, a lot may consist of a single wafer. In this case, a wafer have its names, and they are placed either in a carrier or in a single uh, capsule. Now they hopefully the process is developed and each wafer is processed happily by the operators, and the company make money. And the operator are hands-on. The integrators needs to be hands-on, although a lot of their work is not done on the floor, but actually in front of a computer terminal. You have to make the computer system so that the operators communicate with you through the computer. They don't talk to you every day. You're not on the floor every day. Your goal is to make the routing and so that the operators can complete the whip. Now, there could be a lot of headaches. A lot of times for me, the whips do not move because of limited capacity. Limited capacity is actually not something that your customer like to hear. They want you to have a lot of margins to grow their business, and a lot of times the yield is very low, and a lot of times the quality assessment, quality control also takes too much time and increase the cycle time unnecessarily. Those are the problems that I always see. In the end, those things do matter. The One of the foundry companies I work with, Scorpios, ended up having to pack up and relocate because they couldn't pay the rent of their landlord. And so you see a lot of places that move to places that was formerly occupied by another company. And in semiconductor, those clean rooms are almost transportable, and they are sold from one operator to another. And this is kind of like the hermit crabs in the ocean, moving from one shell to another. Uh, you don't really build a permanent home like TSMC. You actually just move from one to another. There's a lot of cost involved, but you make about $4 million monthly of revenue with very thin margins. The key to success to a foundry, uh, for a foundry to be truly successful, you need to pay attention to the labor and culture, right? A place without labor culture or management culture will have a lot of trouble down the road. Uh, you cannot maintain the lead. If you cannot maintain the lead, then your profit will be thin. If you're a public company, when you have low profit, your stock would be lower, and this can cause a lot of talent to leave. Uh, you want to be in a good location, capable of scaling, but not in the wilderness, right? That are far from a supply chain. You ideally want to have involvement in a scalable product. At least 100 wafers per month is necessary. Otherwise, you really don't have a business. You also have to have the access to capital and stock market to reward key players. Again, without a good lead, you cannot control your product. Without a good volume, you cannot control your cost. And therefore, you don't have a healthy profit, don't have a healthy stock price, and everything just goes down the drain from that point out. It's important to um, remember that if you don't operate well, then you will be forced to move from time to time a lot. The good countries where there's a strong fab culture are United States, even though the cost is high, but it's very close to the downstream of the supply chain. China, Italy, and Japan are very competitive. Korea is very competitive. Malaysia, very competitive. Taiwan, of course.